I'm Christina Astin. I'm a trainer with Physics Partners, as well as a science education consultant and advisor. And so I'm just talking here about the changes to the GCSEs for 2022, which is that the required practicals can be taught by teachers demonstrating them, or by videos and by simulations. And so it's very timely to be doing this session today. It's a session which I pulled together initially during lockdown, because obviously there we couldn't do practicals at all. And so simulations were one of the best ways of keeping students engaged and increasing their skills in doing practical science without actually having access to the lab. So those are the two screen grabs there from AQA and Pearson. Now, a lot of people ask, what's the best way to use a simulation with a class of students, whether they're year 11s or maybe younger? And there are a number of different ways that I would suggest. The first is you can either do it as a preparation before they do the real experiment, or as a follow-up afterwards, especially if we have, as we often do in physics, experiments that don't quite go to plan. Sometimes it helps for students that just need a little bit of scaffolding. So perhaps they're about to do the real experiment. And I think of the more complicated ones, like the specific heat capacity practical, there's an awful lot to do. And so if we can break it down and make it a little bit simpler by showing a simulation, then that's a good way of using them. Some of the simulations I'll be showing you are maybe alternative to the methods you normally use in class. And so, it's showing our students different ways of achieving the same sort of results and capturing similar data. Right now, with your year 11s, you might find that this is particularly useful for revision. So perhaps they've done the experiment for real, or they've seen a video, but showing them a quick simulation is a good way of just reminding them or refreshing them, getting that knowledge sort of back up to the forefront of their brains. And teaching remotely, as I said before, some of us are still teaching remotely. There are teachers off, there are students off, so this is all still relevant as well. Just to let you know, this is what the spreadsheet looks like. And if you access this right now, if you want to, I'm sure Brian can put the link in the chat for you. Let me just talk you through the spreadsheet as it is. On this, on the screen, as you can see at the moment, it's in sort of two big bands, but in the spreadsheet as it is, if you have a look at it, it's just in one big row, but they just fit on the screen. And I've divided it into these four big sort of topic areas. Not that the exam specifications do this, but just to help with your navigation. And you'll see that I have mapped it to each of the three main exam boards. So we've got AQA there, EdXL and OCR. Where there's a slight sort of difference of flavour, for example, specific heat capacity, the very first one you can see there in thermal, AQA asks, just say you need to measure the specific heat capacity of materials. So, that could be water, it doesn't have to be a metal. Whereas EdXL asks about water and then asks students to do a temperature time graph for melting ice. Whereas OCR just specifies metal. So there are some slight different emphases across the exam boards. Underneath that bit, you'll see there are then three rows with lots of links in, and those are links to the simulations. And the top row is my sort of personal recommendation. They're the ones that I think work really well. I've tried to include a range of different providers and approaches, so it's not all just the PHET ones, though I will be showing you some of those today. And most of them are free. There are one or two that have a subscription. I'll tell you about that as we go through, but most of them are free, or at least have a free trial, but almost all of them now, in fact, are free. And I was talking to a developer just yesterday who is about to make all of their simulations free, which is great news for all of us. Just also note that the cells which are, they were in grey, but I can see that the grey has now gone. But you can see next to some of the ticks along the top, it says triple only. So if you're doing triple science, they apply. If not, you can ignore them. Okay, and that's the link where you will find all of those there. Okay, and Brian, thank you, Brian, has put it in the chat as well. Okay, just before we get started, have a think about these things as we go through. From the teacher's point of view, if you wanted to demonstrate the simulation live in front of a whole class, just as I demonstrate these different simulations, have a think, would you do this before or after doing the real experiment? Would you be perhaps demonstrating a more or less complex version of the real experiment? Would you maybe get your students to construct a data table as you go along, and then maybe they can draw a graph and find a value? Alternatively, you might think that a particular simulation I'm going to show you works better if the students are driving it themselves. Perhaps you set it for homework, perhaps you book out a computer suite at school. Think about how you would then introduce the simulation to them. Would you demonstrate it yourself and then let them have a play? Or would you give them very clear instructions, or just literally let them loose? Now, different ways in which you can make sure that the students are doing what they've been asked to do is to ask them to share screenshots of the demonstration simulation with you. And some of the simulations actually ask them to calculate a value, which they could then send to you to be checked. In fact, some of the simulations check them for them, which are really good, really powerful. Okay, well, let's get going. I'm just going to hop between a couple of screens here. So I hope that works. And I'm sure Brian will shout at me if I get anything wrong. So the first simulation, I've grouped them by developer. So we're going to have a look at a few of my favorite PhET simulations first. And we're going to start with the ripple tank. So by the way, that's the page on the Physics Partners website that shows you where the practicals are, including this presentation, which you can access. So here we go. This is PhET, P-H-E-T. Is there anyone here who hasn't yet accessed PhET? You can perhaps tell me in the chat if you are new to PhET. I mean, if you are, I'm quite sort of envious, because it's just such such a great resource. You have a real treasure trove awaiting you. So for this one, we want to click on the slits option, and as that's loading, there we are. We're going to get rid of the slits. We're not going to have any slits, so no barrier there. And you'll see if we press the green button there, the waves just start to emerge. Okay, and you've got lots of different things that you can do there. Now, the required practical asks, for most exam boards, ask students to show that V equals F lambda, so velocity equals frequency times wavelength, and that's what they're using the ripple tank for. Let me just pause that. I'm going to change my camera over because I'm going to do some writing, and you're very welcome to make some notes alongside me. So we've got the ripple tank here. This is the equation that the students are looking to verify, and we can actually measure the velocity and the frequency and the wavelength with this simulation. I'll show you quickly how you'd measure the frequency. So here's a timer. And what we can do is we can set the timer going, but as long as the simulation is on pause down here, it doesn't actually time. And then what we can do is time how long it takes, for example, for 10 waves to pass, and we can use that to find the frequency. So let's do that. Let's count 10 waves. Okay, so go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I tried to stop it at the same point on the wave, but if you want to be a bit more clear about that, you can use this graph, okay, which shows you how the water displacement is changing with time, actually with position, sorry. Okay, so that took 16.18 seconds. So we grab a calculator and we do 10 divided by 16.18 to find the frequency, okay, 0.6162, okay. Now, the other thing we can do is to keep the frequency fixed. Let's get rid of that graph. I'd suggest actually having a slightly higher frequency. and the experiment just works a little bit better, reset the timer. And then what we can do is see whether the velocity is proportional, as it should be, to the wavelength. All right. So another tool we can use is this. This is a tape measure. So let's get those water waves going again. There we go. And once we've filled up the whole tank, as it were, the ripple tank, I'll just pause that. And then we can measure the distance for, how many is that? 1, 2, 3, 4 waves. So 4 wavelengths is 7.2 centimeters. And so the wavelength is 7.2 divided by 4, and that's in centimeters. So that gives us 1.8. So in our table here, we can measure the wavelength in centimeters. We can then, to get the velocity, we're going to measure the distance and the time. Distance, again, in centimeters, and the time in seconds. And by dividing the distance by the time, we will get the velocity. And that, of course, is in centimeters per second. Okay, so our first wavelength was 1.8 centimeters. And let me just show you how we'd measure the velocity. What we're going to do is measure how long it takes one wave to do the whole tank, the whole distance right across there, which is conveniently exactly 10 centimeters. So there's our distance, 10.0. Useful opportunity to remind our students about significant figures here. And then we are ready to time. So I'm just going to put that on pause and start the timer. And we're going to just watch how long it takes one wave to go right across the screen. So just try and keep your eye on one wave. It's a bit jittery, my end. I don't know about you. There we go. 6.24 seconds that took. And so then we take our calculator and we do 10 divided by 6.24, which is 1.60 centimeters per second. Okay. Great. So that's the ripple tank. Hope that's all right. Do let me know if you've got any questions. Just pop them in the chat. And the next one we're going to go on to is refraction. Okay, refraction of light. And let's go on, just go straight into intro here. Okay, so if you've played with this sim before, you'll know what to do. We switch the laser beam on and it refracts as it goes into a more dense medium. In this case, it's going from air into water. Armand, great question. How is the wavelength measured in a real ripple tank? I imagine it must be more difficult with moving waves. Yes, it is, but I can suggest use of a camera here. Even a phone camera. If you've got a ruler, perhaps a see-through ruler, actually in the ripple tank itself, and take a photograph. But it is difficult.
You want to set up, isn't it, the real ripple tank, because you've got to get the depth of the water exactly right, and yeah, can be tricky. So
yeah, it is tricky, but that's one of the reasons why this simulation is a really good way of getting the data.
Yeah, it's so much better.
Yeah, even if you show them the real thing, which I think they ought to see if they're going to do, be asked about it in the exam, but to actually get the data from the simulation. Okay, one thing I like about this simulation is that we can see how the waveform would look. Obviously, this is a bit fake, but just to remind students that the wave is slowing down when it goes into the more dense medium, and that's why the wavelengths, the wavefronts here are getting closer together. But we'll stick with the ray thing here. Now, one way you could use this simulation is to get your students to measure the refractive index of mystery substance A or B. Let's go for B. And to measure the refractive index, which I know not every student has to do, it may be your triple scientists only, depending on your exam board. But what they need to do is they need to measure the angle of incidence and the angle of refraction, and they draw a graph, which I'll show you in a minute. Okay, so this is the way that they would do the experiment. They might measure, as you can see on my page here, they might measure the angle of incidence there in degrees. So that's 10 at the moment. And the angle of refraction is down here. And that looks to me to be about 6. And then they find the sine of the angle of incidence. So we do sine of 10 is 0.174. Let's give it 3 significant figures. It just helps with the graph. Sine of 6 is 0.105. And then we can find the refractive index by doing sine I, 0.174, divided by sine R, 0.105, which is 1.66. Okay. Alternatively, they can carry on. I mean, they should carry on with this anyway. So we do 20 degrees, 30 degrees, 40 degrees, etc., etc., etc. 20, 30, da, 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 da. And then what they can do, I mean, if this is part of your specification, it may not be, they can actually plot a graph of sine I against sine R, and the gradient of that will give them the refractive index. Okay, nice exercise to do if you're teaching this topic anyway. Now, I've got a secret to share with you, and that is that I've done this work and I have, wait a minute, just get onto the right slide. I can tell you that the mystery substances A and B have these refractive indexes, or indices even. So do feel free to jot those down. So this is where your students could actually, you could ask them to find a value, and then you can tell if they're right or not. Okay, now the next practical I'm going to share with you is on Hooke's law. This is the spring extension practical. Now, a word of caution here on PhET. There is a simulation called Hooke's law. I think this one is better. It's called masses and springs. It gives you a lot more control. Okay, so we're going to click on this, which is lab. And if you remember the physics of this, the force should be proportional to the extension. Sorry, that's just gone off the screen there. The force should be proportional to the extension. So what we're going to do is to hang various masses. Can you still see my screen there, Brian? Is that showing you the simulation?
Yeah, that's fine, Christina.
Yeah, okay, it's just it normally has a green line around it, and that's gone. So what we do is we start off by finding the spring constant of the spring, and then we can use that spring constant to find the masses of these unknown red and blue blocks. So that's just a nice little extra to add to it. And the reason that's important is that your students, when they're playing with this simulation, they could change the spring constant. So you wouldn't actually have a correct value for that. So let me show you what you would do. We hang, well, actually, no, the first thing I do is to click on this one, displacement, and it'll show us the length, the extended length of the spring. And here's our ruler ready. Okay, so we hang 100 grams on there, and you can see it bounces up and down just like it would in real life. We don't need this energy graph, we can get rid of that. If you want to stop bouncing, you can just press the stop button here, or you can just damp the motion a lot, and that helps too. And now we can take our ruler and measure the extended length, not the whole length of the spring, but the extension by moving it up to that point there. Okay, so we've got now on my results table, we've got a mass of 100 grams, so that's 0.1 kilograms. That, of course, is a force of what's that? 0.980 newtons. Okay, or maybe you take G as 10, in which case multiply by 10. And then the extension for this one, I don't know, what do you reckon that is? 15, 16, 17 millimeters, I reckon.
Yeah, about that, yeah.
Okay. And then we add a bit more weight. So you can do that with the slider here. So I can increase that to, I don't know, say 150. There we go. So 0.150. That gives us whatever that is, about 1.5. And our extension now has gone up to 20 millimeters. So we carry on with that. And then we can draw a graph. Now, I know that this gets a little bit controversial because the independent variable that we're changing is really f. So it should go along the x-axis here with the extension as the dependent variable. But if we plot them, if you like, the wrong way round, we should get a straight line, at least up to the elastic limit. And then the advantage of plotting it this way around is that the gradient of this, of course, gives us the spring constant K, okay, or the stiffness of the spring. Now, what they can then do is take that mass off, you just literally rip it off, and then you can add one of these unknown masses on, okay, and measure the extension from that. And then from reading off the graph, your students can tell you what they think the mass is, the weight, and then they can calculate the mass. Now, just so that you know, I have the mystery substances here for you. So let me just show you those. The red one is heavier than the blue one. Okay, it doesn't look like it's going to be that way around. So red is obviously made of a different material. So hey, you could give them a bit of a lesson about density as well at the same time. Isn't that brilliant? So red is 370, blue is 230. Good. Any questions about Hooke's law? Aren't you going to get a systematic error from not measuring to the center of mass? Lovely question. The answer is no, because let me just show you. Because the shape of the mass doesn't change, we could measure to the center of the mass each time, or we could measure to the top of the mass or the bottom of the mass, or even the top of the little hook there, as long as we're measuring the change in the length of the spring. That's the important point. And there are a number of different ways of doing that. Actually, you can get this movable line that you can move up and down. So if you take the mass off, you can set that where that is. And then when you put the mass on, you can make sure that you're always measuring to the same place. Okay. I hope that answers the question. Of course, if you did get a systematic error, and maybe your students have done this in the past where they've measured the whole length rather than the extension of the spring, then they'll see that very, very obviously on their graph, which I've now thrown on the floor, so I can't show you, but they should still get the right gradient, shouldn't they, for the stiffness of the spring. Okay, the last PhET simulation I'm going to show you is circuit construction. And this is very useful for doing the experiment about, Ohm's law experiment. Now, the great thing that PhET changed during lockdown is that they added real bulbs. And by real bulbs, you see, you can just tick this here, it means bulbs that are not ohmic. And that was one of the drawbacks before. So here we are, we grab a real bulb. Nobody admitted in the notes that they hadn't seen PhET before, so I'm going to assume you've all done this before, but do shout if you want me to go through it in detail. You literally construct a circuit like this and stick an ammeter in. There we go, and just connect it up. I know the purists would say I can't have an ammeter on a corner, sorry about that. Grab another wire, complete the circuit. I've still got right angles more or less, and there's our bulb. Okay, I always make my students change to conventional current because I just think it's a bit confusing, isn't it, if they're always asked about conventional current direction, positive to negative, and then they see this simulation which shows electrons.
I always think that's one of the most difficult things to explain and get the kids to understand.
So here we go with our voltmeter, and we measure the potential difference, the potential either side of the bulb. There's our potential difference. And then what you can do is you can change, you just click on the battery there and you can change the voltage and you can step it up and make your results table of voltage and current like that, and then they can plot a graph. Okay, and you can do the same for a resistor. You've got resistors there that you can choose. Unfortunately, there's no diode yet on this simulation, so that's not available yet. Great. Now, moving on, I'm going to show you another electrical experiment, which some exam boards require, but not all of them do. Oh, Man, that's good to know that you're new to PhET. I think you'll enjoy having a play with that. Okay, so this next simulation is about how the resistance of a wire changes with its length. And when we do this in the lab, I quite like doing this practical because you get a really good straight line. So, you know, I would recommend doing it for real, but if you really can't, then here's a good simulation. This comes from the Physics Aviary. Now, if you haven't come across them before, they've got loads of fabulous simulations, very, very easy to use, possibly maybe a bit too easy to use. So what we're looking at here is, does the resistance change with length? And you can just click on the wire type here until you get a type of wire that you particularly like. Like, I don't know, what do we have? Do we have gold? And then you can also click on the wire cross section to get whatever cross section you want. I mean, it just changes rather randomly, toggles through various options. Of course, once your students have chosen, or you, if you're demonstrating it, have chosen those two things, the material and the cross-sectional size, you must keep it the same, otherwise it wouldn't be a fair test. So let's write the type of wire here. So we're going for gold. And the cross-sectional diameter is, oh, what is that? 1, 2, 3, 4. So that's 0.4 millimeters, looking at the scale that they've got. And then again, you literally just click on the wire and it toggles through various different lengths, quite randomly, not at all systematically. So our first length there is 6 meters. Okay, you would never experiment with that length of gold wire in the lab. And the wire resistance there is 1.49. I click again and I get, what's that, 7.9 meters? And you could talk about precision of measuring equipment here, only measuring to the nearest 0.1 meters, not very good, 1.97, etc., etc. And if they plot a graph, they really should get a very nice linear straight line through the origin, because resistance and length are proportional. Okay. There are quite a few links to the Physics Aviary simulations on the spreadsheet, so enjoy having a play if you've not seen them before. I'm just going to show you one more, which is on the dreaded specific heat capacity experiment. And as I said, one of the drawbacks of these simulations is that they're quite set up already. There's not very much that the students actually have to do. But what I like about this one is that they can calculate a value and send it to you. In fact, they can submit it and it tells them if they're right or wrong. So they really can't cheat. The first thing I should tell you is that this purple liquid is not meant to be water. And actually, every single time I've done this simulation, I get a different specific heat capacity. So I think it's a different actual simulated liquid every time. Now, just a bit of physics before we launch into that. How am I doing for time? Good. The first thing to say is that we're going to be calculating the energy given to this liquid by using power, electrical power, V times I, times the time that we deliver that power, little t. Okay, so we've got to measure an awful lot of things, and that's one of the reasons why I think this is a really good introduction to this experiment, doing the simulation first. So I would then suggest that we write down all the data down the side here. All right, so voltage, current, time, mass, and delta theta is the change in temperature. all right, you may actually have different letters. If you're doing, I think it's AQA, call energy Q for quantity of energy or internal energy.
I've seen it used that way before.
Bit confusing for you know, students who are struggling with the fact that Q also stands for charge. So two things that don't start with the letter that you're using. Anyway, mass, specific heat capacity, that's the thing that we're going to try to actually find. And then we have to use delta for change in. And then again, your exam board may use T instead of theta for temperature. But hey, you know, it's nice to have a bit of Greece with us today. So what we're going to do is we must make a note of the initial temperature. And the initial temperature, as you can see, is fluctuating. That's nice and realistic. So we're going to have to make sure that we subtract, what should we say that is, sort of 5.7-ish as an average. Okay. And when we're ready, we just switch on the power supply and the timer will start automatically. So here we go. And there's nothing else that students can change or would need to change. A question I'm often asked when we're doing this practical for real is, how long should we wait? And I think it's a little bit how long is a piece of string. You can either just wait until you got bored, give the students a particular time limit. You could make the time a nice round time, like 60 seconds or 100 seconds. Or you could wait until you've got a nice round temperature rise. I think what I will do is wait until we've got a round time of something. In the meantime, let's write down the voltage, which is 77, and the current, which looks to be about 4.7. And there we go. Oh, I just missed 50 seconds. 51 seconds for the time. And the temperature has gone up to 41.3-ish. And the mass is written on the liquid, and that's 225 grams, but we really must have that in kilograms. So it's really important that your students realize that. Okay, let's do some number crunching. So rearranging our equation here, we've got C, specific heat capacity we're trying to find, is equal to VIT, that's the energy we put into it from the electrical heater, divided by the mass and the temperature rise. Don't get me started on teaching this. I ran a session the other day, and in fact our next free session for physics partners is also going to be on numeracy in physics, and I've got a great way of sharing how to teach difficult equations like this, so I hope you'll be able to join us for that. Right, let's put in some numbers. So we've got 77 times 4.7 times 51 divided by a mass 0.225 times the temperature change, which is, do you know what, I'm feeling very lazy and I'm going to do that on my calculator. 35.6. All right, so we put all that in. Let's see what we get. 77 times 4.7 times 51 divided by brackets 0.225 times 35.6, close brackets. How often do our students not do that? 2,304-ish. And that's joules per kilogram degree C. There we go, 2,304. Now, shall we see what happens if we try and put that number in? So I click end, put my name in here, CA will do, and let's put in 2304. Drum roll, please. Great work. Hey, the actual one was 2,252. Okay, my error was 2.31%. Oh, well, that's not too bad. So you could ask your students, for example, to screenshot that, couldn't you, with their real name in full. Rachel, thank you for your question. And yes, I will scan all of the tables that I've done and make sure that you get them. Thank you for that question. Incidentally, if you wanted to take this practical a little bit further, of course, you could ask your students to draw a graph. Some exam boards really like this. If you do a graph of temperature against time, then you should get something which looks like this. There's the starting temperature. Ours was, what was it, 5.7. It will take a while to start to heat up because it takes time for the energy to conduct from the immersion heater to the thermometer. You can see they're using a digital thermometer. And then when it gets really hot, it tails off because it's losing so much energy rapidly to the surroundings. But this straight line bit, you can grab that, and then that is your change of temperature over time, which you can then stick into that equation as the inverse of that term. But the graph makes quite a nice discussion point as well, I think. Okay, now on to a new developer, which I only came across during lockdown. Callum, who is a school teacher, has been developing these himself. And he's given me a code, which he's happy for you all to use as a demo code. It's physics demo. So, oops, physics demo. Make a note of that. It's also on the spreadsheet. That will be operating for a couple of weeks. After that, it's only £50 a year for the whole school. So I think that's well worth it. And, you know, it's nice to support him anyway, isn't it? He just does this as a bit of a side hustle. So I'm going to show you a couple of, actually, no, I'm not going to show you a couple of things. I'm just going to show you one. So let me just toggle through these. One of the required practicals on thermal insulation, which some of you may have to do, works really well on this app, on this website. And it takes them through step by step, but the students actually have to manipulate the apparatus, which is really nice. I'll show you like how it works in a minute. Also, there is a table of results, which either the students can type into, or you can get it to auto type. Now, I think if I was demonstrating, I might get the students to write their own results table and write it as we went along. But if I was trying to save time, perhaps during revision, I might just get it to auto complete. And I'll show you how that works in a minute. And then one of the other ones that's quite useful here is density. Density is quite a simple practical to use, but if you do want a simulation for it, there aren't that many options that I've been able to find. And this one, it does, again, makes them go through all the steps of finding the density of a liquid or a solid, I think. And then the other thing I like about this simulation is that it makes them actually calculate it, and then they have to choose the correct value from a multiple choice of values. In fact, all the different required practicals, and you might have noticed from the previous slide that there are biology, chemistry and physics required practicals. They all have a little task to do at the end. So I'm now going to show you the specific heat capacity one because it makes a nice comparison with the one I just showed you. All the people that you see on the in the app are colleagues of Callum's. So he's made little avatars of all of them. Okay, so it tells you exactly what to do. Here you've got to start by measuring and recording the mass of the block. So I like this in that it does make them do this stuff themselves. So open the data table and you can see that I've got it set up just to autofill the table. Place the metal block inside the insulation. You've got to be fairly good with your mouse on this. There we go. Oh, come on, get in there. There we are. Place the heater into the larger hole. I like this. Look, a little pipette with some water. That helps conduction. Then you put the thermometer into the small hole. Turn the power pack on to turn on the heater. Record the ammeter and voltmeter readings. Again, if I open the data table, you see it's doing that for me. And measure the temperature. And if I click on the thermometer, I get a sort of magnified view of it, which is really useful, and start the timer. So you just click on that and you can accelerate this experiment. I love this too. How many times would we love to have just fast forwarded through a really boring experiment? You know, pondweed, anyone? Yeah, so anyway, it does accelerate. And as you can see from the data table, if I scroll down, it's actually measuring the temperature over a 5-minute period, 10-minute period. There we go. And then it stops automatically, calculate the power of the heater. It's doing this all for me on the data table, but obviously you might want your students to do that. And then we zoom into the sort of theory bit, plot a graph, looks like that, calculate the gradient, There's all the stuff. Let's just guess what it was. Oh no, it was wrong. And then here's the activity for the students to do. They have to just drag and drop these into the right order, and then they're done. And once they've got it in the right order, it tells them that they're right. But I haven't got time to do that now. So that's Science Practical Simulator, it's called, and I really do recommend it. It's great.
Very good, that one, isn't it? For the price, if you get all of those other ones as well, it's very good. Absolutely.
Now, time is moving on, so I'm going to do a couple more simulations, and then if you've got any questions, do let me know. Now, this is a fairly involved one. This is the Newton's second law simulation, Newton's second law required practical. Now, I don't know how you do it in your school, because there are a number of different ways of doing it. And actually, I have managed to find online a number of different simulations. So have a little play around and try to find a simulation which is the same as what you do in school, or maybe you want actually something which is alternative to that. I'm going to show you this one, but as I say, other options are available. Now, this one I like because it really does make the students do quite a lot of work. The setup here is that we're going to try to measure the acceleration, and we're going to show that the acceleration is proportional to the pulling force. And therefore, in that case, we've got to keep the mass constant, again, to make it a fair test. Now, what a lot of students, and I have to say teachers, sometimes don't realise is that it's not just the mass sitting on the trolley that you have to keep constant, it's the whole mass of the whole system, including the pulling weights, okay? So we click on masses here. This is another physics aviary simulation, as you can see. And we're not using a trolley, in fact, we're using, if I just show you, go back, we're using a hover puck. Okay, I'm sure we've all got those in our schools, haven't we? But actually, seriously, if you have a linear air track, it's quite similar to that. It's floating on a bed of air, like a sort of table hockey type setup, with a pulley and these pulling masses here. So we're going to start with our hover puck at 900 grams and our pulling mass of 100 grams. So that's about 1 Newton of pulling force. All right. So the total mass is 1,000 grams. All right, so I'm going to write that on my table of results here. That constant mass there is 1,000 grams or 1 kilogram. And we're going to keep that the same. You might also like to do the experiment where you keep the pulling force the same, but change the mass, okay? But I'll show you this one. So we return to the experiment. Okay, now the next thing to notice is the length of the card sitting on top of the puck, which is going to go through light gate 1, and we'll measure the speed through light gate 1. And then it's going to go through light gate 2, presumably faster because it's accelerating. And we're going to need to know the distance, which is the length of the card, 17.4 centimeters, and the time it takes cutting the light gate at each light gate place. All right, so I press start here, and you will see that each light gate triggers the start of the card and the end of the card. Watch what happens. So here it goes. This isn't real time. It would be accelerating, perhaps, I don't know, faster than that. Who knows? So at 11.21 seconds, the first light gate was triggered. That's where the card first entered light gate 1. And this 11.4342 is where that card left the first light gate. Now, if you do this in school, you may well have an interface which connects with a laptop and it calculates this for you. But I think this is quite a nice opportunity to show the students how that's actually working, you know, the internal workings of that. So this was a force of about 1 Newton, wasn't it? It was 100 grams. So I'm being a little bit lazy and using G as 10. Now, to find the initial velocity, we've got to take the length of the card, which I've just forgotten. Was it, Brian, you didn't happen to remember to do, was it 17.3? It didn't show. Okay, I'm going to,
sorry.
No, I'm going to do it again. 17.4. Okay, 17.4, close. Let me just reset and do that again. Okay, start, here we go. So that's the distance, and what we're going to divide that by is the time. And the time for this, all right, is 2.4472 minus 2.2310. Okay, that's the time that the card was cutting the light beam. So that's the time it took to go through the light beam, 0.2162 seconds. So I take my 17.4 and I divide by 0.2162 and I get 80.5 centimeters per second. Okay, that's how fast it was going through the first light gate. So that's what we call the initial velocity U. For the final velocity V, we do exactly the same thing again, but this time it's going to be 17.4 divided by 2.9008 minus 2.7634. That's 0.1374. 17.4 divided by 0.1374 is 126.6. Okay, so it's sped up. It's gone from 80.5 to 126.6. Now, what was the time taken for that change? Now, strictly speaking, what we should do is take the middle of the first two numbers and the middle of the last two numbers. But again, I'm going to just be slightly cheaty on this and take the number at 3, 2.7634 minus the number at 1, 2.2310, and that's 0.5324. Okay, it should really be the middle of the card as it went through the first light gate and the middle of the second light gate. It doesn't make too much difference, at least not to a couple of significant figures. Now, to find the acceleration, I'm going to use the equation, let's write it up here, A equals V minus U over T, change of velocity over change in time. And so that is going to be 126.6 minus 80.5 equals that, divided by 0.5324 is 86.6 centimeters per second squared. As I say, if you don't think your students are going to cope with that sort of level of intricacy, then there are definitely some easier options available. And there are different setups, as I say. So there are some where you've got an inclined plane, others where it really does look like a trolley. Just have a look at some of the other links that I've put on the spreadsheet and you'll see what I mean. Now, I've saved my new discovery till last, and I'm just going to have a look down the people here to see if our developer has made it. No, I was hoping that he might be able to come, but he was going to come yesterday before we changed the date and the time. So this is a new simulation that I have just come across called Flashy Science. And again, we've got a freebie login, which I'll show you. Actually, I can show you right now on the slides. Here we go. So flashyscience.com. And if you log in with this fake email address, don't try emailing me on that. It doesn't exist. astinteacher@astinconsulting.com. I didn't make it up. This was the developer when I spoke to him yesterday. And password Flashy Science with those capitals as typed. And that will expire on the 30th of April, by which time I am assured they will have unlocked everything to be free for everybody teaching school age students, that is. So I think that's a really fantastic deal, and I recommend you have a look, because they are lovely simulations, as I will now demonstrate. So you can search by physics, chemistry, etc., etc. So we want physics, and we want level 1, which is GCSE. But let me just actually show you all the other things that are there. Okay, quite a lot of useful stuff. Yes, Brian might be able to put the link to the details there, Reaper, but they are on the slides, which as I said, are already on the website. So I'm going to show you the Leslie cube. Now, this is a curious practical for lots of different reasons. And if you ever go on Twitter and ask about the science behind the Leslie cube, measuring infrared radiation coming from a hot object, you'll get a lot of physics purists who have quite a lot to say about it. But I'll spare you that pleasure, and we'll just do it. So we press go, and here we go. And just to let you know that previous page that I showed you, there are worksheets available. There are lots of instructions. It's really full of really useful stuff. Okay, so to do this experiment, we first of all have to boil the kettle. So you click on the kettle and switch it on. If I had a slight criticism about this, it's not always obvious what to do. So you do need to read the instructions. And if you're like me and you just think, oh, I don't need to read the instructions, I'll just get going, you might get unstuck. Okay, so we pour the hot water into the Leslie cube. It just automatically puts the lid on. And this is the detector. And I recommend that we start with the detector a little bit further back, because it'll overload our poor little voltmeter here. Switch the voltmeter on, the multimeter that is. And I like the fact that there are different settings on here. And it's the DC volts that we want for this experiment. So switch on the signal amplifier, which is basically what the detector is connected to, which converts the infrared signal into a voltage that we can measure. And you'll see that with the matte black side, surface 1, pointing towards the detector, we're picking up 110-ish millivolts. Again, I like the fact that the simulation is showing the fluctuation, because that's real. And you can see that if you move the detector, of course, the voltage changes. So you need to keep that fixed through the experiment. And I like the fact that when you click on it, you get that magnified thing up above. Okay, so then we just click on the Leslie cube to try a different surface. And one thing that you need to be careful of if you're doing this for real or on the simulation is check that your temperature is staying constant, because if I click on this, you can see that the temperature is, as it really should be, gradually diminishing. So for that reason, it's important to do some repeats. So do your 4 surfaces. We've got shiny metal, matte black, white, and whatever that is. It says on the worksheet anyway. Yeah, repeat it so that you make sure that the temperature isn't affecting your results. Now, just before we finish, I just want to show you a couple. I'm not going to demonstrate these, but I just want to make you aware that there are a couple of other very nice developers around that are worth a look at. One is called ophysics.com. Again, these are on the spreadsheet, so you'll find them. This is for those of you that are doing the exam board that has standing waves. So here we've got a frequency of about 62.5 hertz and a standing wave there. If I double the frequency to 125-ish, there we go. We get our next standing wave with more nodes and antinodes. Okay, loads and loads of simulations on this website. Some of them are a bit A-level-y. So if you're teaching A-level, you know, these are brilliant. As you can see, lenses, electric fields, all sorts of things. And then so some of the fun stuff will blow your mind. Is just, as it says, fun. And then another developer I want to just share with you is Physics Classroom. And again, you can see lots and lots of different interactive topics here. I've just chosen this one because it comes up as a required practical in some exam boards, and that's the law of reflection. Who knew? So this is, to be honest, this is more of a tutorial than an interactive simulation, but you have to fire the laser and, you know, you can drag the laser around and investigate what happens. That's quite fun. Okay. Now, I haven't talked about videos because this was a session on simulations, but if you haven't come across the Malmesbury education videos.
In this investigation, we will be looking at the resistance of a wire and how that resistance changes with the length of the wire. They
seem to have managed to get all their teachers to take part in making this. I'm just going to switch my camera back on. But I also want to tell you about the wonderful films that we made at Physics Partners. There are 12 so far, a few more still to come. I hope you can still see my screen there. So they are on all sorts of topics, but particularly the difficult topics, the topics which are quite difficult to teach. They're all about 10 minutes long, made by our lovely trainers. And hopefully they, you know, if you were going to be teaching, say, nuclear fission next week, you would hop onto Alan's wonderful video there that has a reference to cake, very important, cake. And you would feel a lot better prepared for teaching that topic. I guarantee it. Oh, that is just a screenshot of part of the worksheet that you could pick from Flashy Science. Very, very useful, those worksheets. VP Lab is a very involved and wonderful set of simulations that have been around for quite a long time now, though they're updated all the time, but you do need to download some software. So it's a little bit harder to access perhaps than some of the simulations I've been showing you. And I have to say, they don't work brilliantly on Macs. So if you're a Mac person, that could be a bit of an issue. So we've just got a couple of minutes if you've got any questions, but I would love some feedback on this. Just grab this QR code, or Brian's just put the link in the chat, and feel free to, yeah, lob me any questions.